How many of you want to compete in the North American qualifier? It's just like a mock competition. You have one,
Yeah, I
two,
think I agree.
three, okay. I want to form, so it's a 3-person team. So either we have 3 or 6, we have Gian who's also up. So we have 4 for now. Ian, you could compete perhaps. Oh, you're not a student anymore, so. You're a student now?
No,
You're not.
I might still be able to, but.
You might still be able to.
No, the qualifier, right?
It's a qualifier, so, so why don't you get on some team and maybe, help them with,
Yeah, I can still be
Yeah?
like
Okay.
officially.
that'd be good, so that's 5.
I already have a team.
You already have a team with 2 people, so do you need one more? That might be good,
I don't
yeah?
know compete myself
good.
because I have an exam the very same day, so it's just 2.
Uh-huh. You're not gonna compete?
I can't, I have an exam the very same day.
Uh-huh.
It's the 30th, right? The qualifier.
It's the 30th, right?
We are 5th.
Yeah, I believe so, yeah. Whatever that Saturday is.
Yeah.
Do
So.
they have to do the qualifier to do the ICPC or?
No, it has no relevance to
Okay.
the ICPC. Are you interested in competing in the North American qualifier? So so we have 1, 2, 3, 4, sorry, you have 2 you said. 1, 3, 4, 5, 6, 7. You have 7 people. We have to find 2 more. Can we convince you?
I'm still on the fence about it because
Sorry?
I'm still on the fence about it
Uh-huh, why?
because of my time availability. I have a very tight schedule right now.
Uh-huh. Well, how can we convince you?
Just do it for.
Yeah.
I think it's cool. I would love to. Like I definitely would have a drive for it, but like I have so many responsibilities at the moment. I'm like kind of juggling how I can fit.
These things will happen all the time.
That's true.
They're not gonna go away, they'll get replaced by some other responsibilities, so life goes on. You just have to decide, okay, this is important for me, I think it'll be fun, I wanna do it. That's all you need to
That's
decide.
true. I'm thinking about
Did I
it.
convince you?
I'm thinking
Maybe.
about it.
Nicole, are you a student anymore?
Yeah, I'm a master's student.
You're a master's student, okay, so we could recruit you as well. So, all those who want to be on a team, today, I need you to talk to Gian. We'll form, if you don't have a team already, we'll help you form a team. What we can do is try and distribute people who know a little bit more in all the teams. That way, we'll have, because our goal is not necessarily to excel at this competition, the qualifier, but to get enough people excited so that you will help that you will get excited about training for the next competition. So you two, I forgot to ask you, would you be interested and willing and able?
Yeah, I'm available.
Great, perfect.
However, I do
Yeah.
have a question. Like, is there? Okay, I just need to understand exactly what the competition is and what I would
Okay.
need to know, like, for.
Right, so this is a programming competition. It's on the 30th, and it'll be, I don't remember the exact time, it may be from 12 to 5 or 1 to 6 or something like that. You'll be given a bunch of problems. I believe it's all online, if I'm not mistaken. And you and your team need to solve as many problems as possible.
Okay.
And if you've attended any of the mock competitions on Saturday, it's no different from that. You'll be given similar problems with similar descriptions, and you write your program in whatever language you want, you submit it if your program is right. And if it passes all the tests, then your team gets 1 additional point for solving a problem.
Okay.
And
So from the-
as a team, you try and solve as many problems as possible. Preferably you try and take on different problems, Or if you think you're very close to a problem, you talk to your team member and figure out, you come up with some ways to somehow fix the problem, and that way you could even jointly solve things. And for things to happen in this collaborative way, it's better if you're here physically at the lab, and then you can actually talk to people instead of having to send messages and emails and texts to figure out what the problem is. But you know, if you can't come physically, so be it. You can still compete, and you could still get the benefits of, you know, of the competition. And even if you have an exam, you know, you could.
I'll try.
Just kidding.
It's only one, otherwise I will go.
Yeah.
September 30th.
Good. Yeah. So looks like everyone here has agreed. So that's fantastic. So that's looks like we can form maybe 3, maybe even 4 teams. We have to register you, so please let us know. Yeah. Sounds good. Okay. So do contact him at the end of this session, or do you want to do that now because you have to run at the end? No.
I think I'm gonna, if I can't, if there's anybody I
Let's
can't get to.
let's pass the sheet around. Can I borrow the
Yeah.
sheet? Right? Or do you want to just send a message on Discord to Jian? To have his, that would be easier, right?
Yeah.
Okay, so if you can send it now, that would be great, while I set up things and get this started. By the way, thank you for all of this.
Of course.
There was,
I have a quick question.
yes, Nicole.
For the trainings and stuff, is it only on Saturdays? Because I do have Saturday classes,
Uh-huh.
so I don't know if I'd be able to attend those trainings.
You mean the mock competitions?
Yeah.
So the mock competitions are, they're in the afternoon from 12 to 5.
Okay.
If you have class at that time, well, first of all, it's online, so you can do it from anywhere.
Yeah.
If you do it between 12 and 5, then there's a competition feel to it.
Yeah.
You can always do it afterwards.
Okay. Yeah.
Yeah, and essentially compete against yourself.
Okay. Sounds good. Thank you.
Jian, what do you need from them? Like just name?
Yeah, what do you need from them?
Email?
When I went to the registration form, I think I just saw names and emails, so like.
Do they have to go and register? Do you remember the email?
I clicked on that link that you sent in the Discord, and it said, I saw something in red that said like only a coach can register teams, so I didn't do anything,
Okay.
just in case. So I didn't wanna mess with that.
Yeah, no, I can register you, but but you
Yeah, I
have to
can-
tell
I
me
can-
what I need to register.
Yeah, I
you
can
as.
collect, names and emails.
Okay, is that all, or do they have to go to ICPC or something like this and register?
I'll check the
Anyways,
link that you sent.
if they all send you messages, you know how to reach them. Please give us your name, and maybe your, what else do you need? Your Discord handle, so that we know, you all have strange names and there's no way for me to figure out who you are. There was one other thing, all of this happens under the umbrella of an entity called the Academy for Computer Science Education, where we focus on training you guys for various programming things and problem solving skills. But we also do a bunch of other things. I run workshops for school teachers, for K through 12 teachers. So if you're from local, if you graduated from local schools, some of your teachers may have come to us and gotten training from us. We train them for their teacher certification exams, we train them for just general skills, we teach them on new topics like AI and IoT and this and that. So, so we do a lot of these different things, and this entity is something that I run with the help of Nimi here. I am looking for more student help for many of the activities, and a lot of these activities happen on Saturday. So if you have time, and if you want to make some additional money, do let me know. I'd be happy to sign you up for some work. And many of these involve coming here on Saturday when we run these workshops and helping us with the logistics of running the workshop. Okay. So if you're interested, send me an email. You know how to reach me, right?
Yeah.
I'm Giri at FIU.edu. Okay. There was, one other thing that Anne reminded me that we need to do.
Yes, the competition
Right.
t-shirt.
So, we're trying to get all the teams to the programming team students a t-shirt that tells people that you're with the programming team. It's the only way to brag about us. And, people don't know about us. You already know this, right? You need to tell everyone what an elite group you belong to, and what a bunch of crack shot programmers you guys are, problem solvers you guys are. So we want to design a t-shirt. We need help. None of us are really artists. We have very little skills, but now you even have AI that can help you do whatever is needed. Just don't take copyrighted images and give it to us. Create a logo, and the winner will get some kind of a prize. It'll be on every t-shirt that your team will have. How does that sound?
Yeah, good.
But you need to get it to me soon. So maybe by the time we meet again next week, if you can send me some attempted logos, that would be fabulous. Yeah?
Yeah.
Okay.
All right. So I want to quickly again recap the things we did last time. You remember some of this. We looked at a problem called Findmax, and we looked at many different versions of this. The first version is a simple version that says find me the largest item in an array, right? And this is the easy case, and we know that there is a simple solution that runs in time because it's a simple for loop. And we also know that this is optimal. You cannot do better than this. However, there are query versions that are a lot more interesting, where you need some more additional skills. In query version, you're given a range, and you're given a start point and an end point, a start index and an end index. Your job is to find the largest value within this range. And if you don't do any pre-processing, then every query can take a long time because you have no information, you don't know what is where, so you end up searching the whole thing. And if the range is large, this could take you big O of n time. If you're running k queries, the whole thing could take you k times n time. On the other hand, if you prepare a lot and you store every possible solution for every possible range, then you can pre-process that in n squared time, store that in n squared space, but answer the queries in constant time. And so running k queries can end up taking you only k plus n squared. We spent a lot of time trying to figure out a third version where we used a tree structure and figured out that this tree structure is a nice balance between these two crazy versions. One where you don't do any pre-processing, but it costs you a lot for queries. Another where you'd spend a lot of time doing pre-processing, but your queries are super, super fast. So here, you find a nice balance between the two. We spend less time, not so much crazy time doing pre-processing. We don't spend a lot of space doing pre-processing, but we end up answering queries reasonably fast. It's not quite constant time like this, but it's log n time, which is really quite fast. So if you have k queries, it becomes k log n plus n as the total time for total cost of queries and pre-processing. This is something that we found useful, and we started to look at a second problem, where the problem was actually quite different. Here we were given a sorted array with repeats, and our task was to, oh, I need to get away from this. And our job was to find what's called as the mode, which is the most frequent item within the array. If you're finding this within the array, it's easy because you just go in and count the frequency of everything there and report the one that's needed. So it's easy to do this in linear time. If all you want to do is to find the most frequent item in the entire array, because you just go left to right, and all the equal items are next to each other, so you can keep track of a count, you can keep track of the highest count, and then eventually, by the time you finish up, you'll have the answer. So relatively easy. It still runs in big O of n time, and it's quite fast. However, if I turn this into a query version, then things go a little bit crazy. Here in the query version, you're still given the same array, but you're asked a range, and you're asked to tell us the most frequent item in this range. And again, very similar to what we did before, we can consider the case where we do no pre-processing, and also consider the case where we do lots of pre-processing and store every possible answer and report this in constant time. So we want to know, again, is there a middle version of this? There are actually several middle versions of this. So by the way, that's an example of an array. It's sorted, and there are lots of repeats, right? So what do we do with this? So we want to find the mode in a given range. The first idea we have is to instead of storing this big array with lots of repeats, what if we made it more compact and only stored one copy of an item, but we also stored its frequency, right? This was an idea that we had, and now this kind of helps us with the query because there are natural breaks in the array. You can see that I can break it up where these are all the ones, these are all the 3s and the 6s and the 9s and 15s and so on, right? So instead of keeping track of all 4 items, I just have to keep track of one item along with its frequency. So I can make this more compact, and this could be helpful if there are quite a few unique items. And if I were to do this, then I could write down that I have 2 copies of 1, I have 4 copies of 3, 1 copy of 6, 3 copies of 9, 1 copy of 15, and so on. So essentially, I have both the item and its frequency. So if I want simply the most frequent item in the entire array, I just have to look at the frequencies, and I know immediately that 3 is the most frequent one. If I give you a range, well, I can still do the search in this new array. It's a little bit more. It's a little tricky. I have to take care of some details, but it's possible, right? So if I tell you that I want to find the most frequent item, say between 3 and 10, then you'll have to do some work in order to figure out where exactly this sits, right? It's not going to be trivial. You will know that the first 2 items are 1, so if you're starting from 3, you're taking into account all these 3s. And if you're ending at 10, it'll be somewhere here, because that's where it'll be 10 items. So you have to kind of count, you have to keep track of things. It's a little bit more work, but it is still possible to do it. The good thing now is that you have a compact array, you have a much smaller array. And this means that I could go back to my previous solution of the 2-dimensional matrix, right? Where I'm trying to say for every possible range I want to figure out the answer. Well, at least I can do this for all the items here, and all the start points that are here. I can quickly compute the ranges and have the answer. Now, if the range you're asking doesn't quite match, if it is between, if it starts somewhere here or if it starts somewhere here, then all we have to do is to readjust things for the first group, and we can kind of figure this out. So it's a little bit more work, but it's possible to do this, right? So that's really what we want to do here. That's one of the approaches, and if we do this, then I'm going to not go through all the details, but you can see that there is a version of this earlier problem where my time complexity now depends on how many unique items I have, right? Here I have 7 unique items from the original 15, so I'm going to call this array as being of size n, this array as being of size m. So really the query now, the pre-processing will now be proportional to m squared, where m is the number of unique items, right? So the whole processing now becomes n plus m squared, and space becomes n plus m squared, and I can still answer queries fairly quickly, but with a little extra work. This big O of 1 actually is a little more work than this. You have to really take care of a lot of minor details there. Okay, so in the end you get time complexities that are slightly better than what you had before, but not by much, because the number of unique items may not be that much smaller than the original size of the array. So what we're going to do, what we said we will do next in last time's lecture was to say, what if we were to do this with a tree? I don't think we went through all of the details here, correct? Is that right? Or do you remember at all, anyone?
We started looking at it.
Yeah.
But I don't think we went.
Okay, but I don't think we went through all the details, right? So the last idea we have is to use a tree and see if we can do things that are much better. It's going to be much better in terms of the time complexities. You're not going to see any squared anywhere, and it'll be hopefully a lot better. So in this last version where we use a tree, we start with things that are somewhat similar. We start with the original array. We also calculate the compressed array with the frequencies, and we're going to try and answer things over here. Now, the way we're going to work this out is actually quite simple. By the way, just to get you a big picture, we want something like what we did before. We want pre-processing time to be smaller, and we want the query time to be slightly higher than the previous version, right? That's the general idea. So we know we want a tree, and I showed you last time that the way we're going to do this is, in the earlier version, we took the array and simply slapped it at the bottom layer of the tree. This time, what I'm suggesting is, instead of putting it at the bottom of the tree, let's compress it and then put it in the tree, right? And remember, the compressed version has unique items and frequencies, and so those are your unique items. You've got 1, 3, 6, 9, 15, 24, and 39. We also have frequencies, and so we're actually going to also figure out that this part, all the ones sit in the positions 1 and 2, 3 sits in positions 3, 4, 5, 6, 6 sits in position 7, 9 sits in positions 8, 9, and 10, and so on and so forth. So all this detail we can note down somewhere, right? So all this becomes useful in how we're going to manage it. Now the good thing is that this compressed array will put it at the bottom level of the tree, like what we did last time. And then we're going to take them in pairs and store useful information as we go up the tree. So we're going to create this entire binary tree, right? Just like before. But now we're going to take these two pieces and merge them here. This one was in positions 1 and 2. This one was in positions 3, 4, 5, 6. So therefore, this is going to merge all those positions. It's going to be 1, 2, 3, 4, 5, 6. All right. And here we're going to say that the most frequent item in this portion of the tree is the item 3, and it has frequency 4. Okay? Same thing over here. We've got 6 in only one position and 9 in 3 positions, and therefore 9 is more frequent, and that's what we write down here, and the whole thing stretches from position 7 through 10. And so if this goes from 1 to 6 and this goes from 7 to 10, you can see that up here it's going to go from 1 to 10, right? So similar things happen, information flows up the tree, and you have captured a lot of useful information, and the question is, how are we going to use this to answer our queries as quickly as possible, right? That's where all the hard work is. And so that's the next thing we're going to look at. Any questions so far? Are you with me, or is this getting pretty heavy? Well, you've seen this before, so this is hopefully quite easy. So I've described this before. A lot of our tree-based work is to, if we are looking at a range L comma R or I comma J, it doesn't matter. We first locate the left end somewhere in the tree. We locate the right end somewhere in the tree. And then we look at all these pieces, all these subtrees that are hanging off of the tree, and extract information from there and quickly figure out the answer. That's the whole idea. Now, since we are interested in the range L comma R, which means everything between L and R, that means we're only going to be interested in all these green subtrees because they hang to the right, right? Those are all going to be either in position L or to the right of L. Same thing for these guys, this part of the tree. All these are going to be to the left of R, so therefore we want all the green subtrees and leave out all the red ones. Okay? So, and for any subtree, we only need the information that's at the top of that tree. We don't need to go and go through that entire tree and figure things out. So that's the good thing about the way we've processed and we've pre-processed the whole tree and stored information. And all of this needs to end at some common ancestor, which may be some node in the tree. It may be right at the top, but we don't know where it is. Okay? So using this principle, you'll see that there is a nice way to handle things. So let me show you the whole tree again. And let me start with an easy case. Supposing I have an easy case, I want to find the most frequent item in positions 3 to 10. Okay, now let's see how we do this. So this is our L, this is our R, right? So we are going from position 3 through 10. Now the good thing about this choice of 3 and 10 is that 3 starts from, all the 3s are included, and 10 breaks between 9 and 15, so all the 9s are included, right? So that's why it's easier. So let's see how we work this out, and then we'll hopefully take care of the other case when it's not nicely sitting at these breakpoints, yeah? So 3 and 10. The way we're going to, I just explained it to you on the previous slide. We're going to first locate L, then we're going to locate R, and then we're going to do some processing. So that means we're first going to locate 3, then we're going to locate 10, and then figure things out, right? So when I locate 3, what happens? Well, we know that 3, I have to start at the top of the tree, and I will follow that path until I get to 3, right? Are you with me so far? And that's easy to figure out because if this is at 1 comma 15, I should be going into 1 comma 10, that's where 3 is. This is where 3 is, it's in 1 comma 6, and it's in 3 comma 6, so that's where I need to be, that's where I will end up. Fine? Then I'm going to do a similar thing for the right end, yeah? So I'm going to look for 10, I'm going to do the same thing, and when I do that, it starts again over here, and I can actually stop here because everything here is included in this subtree. If you want, you can go all the way down here, but it really doesn't really help you that much, okay? So we've located 3, we've located 10. Now we know that these are the 2 paths I need to look at and process it the way I showed you earlier. You have all those green subtrees hanging and the red subtrees hanging. you throw away some things and you look at the ones that are remaining and you have the answer. So just by looking at this, I should be able to figure out what is the most frequent item. And it's actually quite easy. You have this node that's included, so this says 3 is the most frequent item and its frequency is 4, right? Then when you go here, that side is not included, so whatever it says, I can pretty much ignore, that's not relevant. When I go here, again, I've already, it's not telling me anything new, so I don't have to do anything anymore. Then as I go down the green side, it says here that 9 is the most frequent item and it appears 3 times. And then I don't have to look anything below because it already has the complete information that I need. So now all I have to do is to find which one is better, 3 with frequency 4 or 9 with frequency 3. Obviously 3 has higher frequency, and so that's what I'm gonna report, okay? So all I'm doing is looking at these 2 paths and I'm figuring out the answer. Is this clear? So this is the easy case when your left and right points nicely sit where it chops where it doesn't go and cut off some other repeats, right? Are you with me so far? Okay, so now let's look at the harder case. What's a harder case? Well, for that I'm going to use this screen and do that.
Can you explain the actual condition we would use?
The what condition?
So I understand why we're going left, but
Yeah.
in a like pragmatic way of
Programmatic way.
Thank you. Yeah.
Uh-huh.
How would this really look?
So you're gonna, it all depends on how you use information stored in each node.
Okay.
So here, this tells you this node here is lording over an entire range going from 1 through 15. Great. Then it says in this entire range 1 through 15, the most frequent item is 3 and its frequency is 4. This is the information I have at that moment. Now, I have to make a decision here. If I'm searching for 3, I have to make a decision whether I want to go left or right. Well, the way I would do this is, I would say, let me go down left and see how it goes. And see if 3 is in there. Because I know the range this takes care of. This is 1 through 10. And so 3 is in there, so I'm fine. Otherwise, I go that way. That's all. So there'll be a simple test that'll tell me whether to go left or right. That's my left or right test. And then as I go down, if I'm doing the left-hand one, I have to keep track of all the right subtrees that I'm skipping over, because those are the ones that are going to give me useful information. As I'm going down the green path, which is the right end, I'll keep track of all the left subtrees that are going to give me useful information. And if I have all that, I will have the answer. I just pick the one that's highest frequency among all of them.
Yeah. If you're basing it off the 3,
Yeah.
Is this the 3 index?
It's all about the index.
Yeah, it should be.
Correct. So 3 and 10 here correspond to index. So this says in the original array, go through index 3 through 10, tell me the most frequent item,
Yeah.
right? And it turns out that the answer also is 3. Yeah, let's not confuse the index and the, yeah, all right.
Okay, thank you.
Okay, so then let's now talk about how to deal with a harder example. So instead of 3 to 10, let's take 3 through 13. Actually, let's take 5 through 13. Okay, so that's the range I want to look at. Fine. Clearly, it doesn't nicely fall between things, and so we have work to do. And the question is, how do I do this? So here's how we're gonna do. We're gonna follow the same strategy, and the strategy is first locate 5, then locate 13, and then do some processing and give us the answer, right? That's the idea. So I start at the top, so let's look for 5 first, and then we'll do 13, and then we'll have all the processing. So 5, I start at 1, 15, it says go to the left, fine? So I'm starting here, I'm going to the left. And I go down to 1, 10, and it says go to the left for 5. So from here, I'll go to the left. and I've got 1,6, and then it'll say 5 is over here, go to the right. So these are my choices so far. But here, unlike in the previous case, 3 doesn't take care of this entire subtree, right? It only takes care of part of it. How do I use that? Well, the way I'm going to use that is, since 5 is the left end, I have to go and do some little counting here. Now, I'm only interested in the subarray 5 through 6 instead of 3 through 6. So therefore, the frequency of 3 is not 4 anymore, but it is 2.
Yeah.
Because 5 through 6 is only 2. Is that clear? So I'm doing a little extra work. So instead of just reading off this number 4 as the frequency for 3, I'm going to read it off as 2. Okay, great. So the information I got from here is that I have item 3 and it appeared twice. Fine? Are you with me so far? Okay. Then as I move up the tree, I don't have to worry about anything on this side because it's outside my range, right? So I won't even bother looking at anything there. I'll go up here. There is a subtree on this side that's of interest, right? So I have to know what I skipped over here, and so that's this part here. This entire thing will give me an answer, and it'll tell me that 9 is the most frequent item in the subtree. I don't even have to go and do the processing and the calculations. I already figured that out, and I know that the best thing here is 9 that appears 3 times. So by now I already know that this is better than this, I can ignore this. So for now, the winner is 9, 3. 9 that appears 3 times.
If we're only looking at 5, do we actually check the right subtree? Because the right subtree is outside the range of 5.
I'm looking at remember I have 5 through 13. So there will be a separate one on, so actually these calculations I will do later on. So I jumped the gun a little bit. If you want, we can come back to this and explain how these values are used. So let's go back to the right end, to the right side. We have to look at, we start searching for 13. Now, if I'm doing searching 13, I'm up here. Clearly 13 requires me to go to the right, yeah? So I go right. And then it says 13 is in this range, so it's asking me to go left. So left. And then 13 is over here, again now to the right. You're with me so far?
Yes.
Okay. And I'm down here, and again 13 doesn't include this entire piece, so I would have to do a little bit of calculation. This time I have to I'm going to notice that 12 and 13 are in the range, not the other side, right? And so therefore I will have 24 that appears twice. Is that clear? Everyone okay with this? Yeah? So the information I'll get from here is going to be 24 that appears only twice. Fine? I had to do a little bit of work, a little bit of processing here because it didn't cut cleanly. It involved some extra work. And these are the things that you have to think about how you're going to code it up, but it's not terribly complicated, right? Okay, good. So now let's go back to the processing that I was telling you about. We've got 3, 2 here. Here we have a right subtree that we missed out. That's going to give you a 9, 3. If the entire right subtree here was useful, then we would have just taken the answer over here and stopped. But it's not the entire subtree that we need. In fact, this entire subtree is not enough. We have to stop at 13 somewhere. So we have to go down this tree and see what else is needed. Now over here, there's going to be some right subtree not relevant, right? Yeah. But there will be a left subtree here that is of interest because it's in the range, correct? So this left subtree corresponds to that guy over there, right? And that's 15 with frequency 1. So the information I'll get from here is from this side, it'll be 15 with frequency 1. When I factor this in, we know that 24 with frequency 2 beats 15 with frequency 1, right? So we move that up. Over here, there is nothing to process because this is outside the range. Over here, there is nothing to process. So now we have two winners from both sides. From this side, it was 9 that appears 3 times. From this side, it was 24 that appears 2 times. And the winner is
9.
that guy there. And so our answer would be 9 that appears 3 times. Now, how fast was this? Didn't this sound like way too much work? Well, it is, but you have to imagine that this tree is very, very big. So the nice thing is that the tree will be of height log n, and if you have hundreds and hundreds of items at the bottom, that tree will still be log n height, and the amount of work you do will only be proportional to the height of this tree. And you can convince yourself that we're doing only log n work. In fact, we ignore almost most of the tree except for 2 paths, and both these paths are of length log n. And so the amount of work you do is proportional to log n. And that's how you get the time complexity. Are you with me? Questions? Are there things that are not clear?
I still don't understand how you know to get the right subtree. I guess you just automatically get it if you're not getting the left one, you take the right one.
That's right, yeah.
How do you
Remember,
figure
every
that?
node is looking over some range, has information about a certain range. That range got broken into 2 pieces, a left piece and a right piece. If you're not in the left piece, you are in the right piece. Right?
Yeah.
And you can see here, there are no overlaps. If this goes from 1 to 6, this goes from 7 to 10. If this goes from 7 to 7, this goes from 8 to 10. No overlap. Okay? Because these are indices, they're all integers, so it's going to be a clean break. And they're all contiguous. So 2 adjacent subtrees are going to have adjacent indices. Right?
Mm-hmm. Yeah.
So it'll be very clear whether to go left or right.
Is the time complexity for the query itself still linear? in
Sorry,
this
say that
case?
again?
Is the time complexity for the query itself still linear?
No, that's my query. My query is 5, 13.
Yeah.
For 5, I have to locate it. That took me log n time because that's how I find this path. I have to locate 13. That also took me log n time because that's the path. And then I process that much information in each node. And so again, my total work is log n. So I can essentially process this query, and I gave you the answer that 9 is the most frequent item with frequency 3 with log n amount of work. Yeah, fine?
Would you ever clarify again on the frequency for 24? Are you getting the difference between the balance,
Yeah.
the max balance?
So you know, imagine that you're in some node there,
Mhm.
and there are 2 numbers there. So let's say x and y.
Mhm.
Okay. So you're down there at some node, and you're looking at a range that says this node takes care of indices x through y. So we're in some range in this array.
Mhm.
But you're told that R falls right in between somewhere.
Yeah.
Okay. Now it depends on whether it's R or L, because with R you have to take care of the left piece, with L you have to take care of the right piece. So let's do the argument with R. It should be similar with L. If it's R, then I'm going to break this this range as x comma r because I don't care about the rest. So since all of these are the same value, I know the frequency. It's exactly whatever number of items there are in this range, which is how many?
R minus X.
Plus one.
It's r minus x plus 1.
Oh, yeah, plus.
Okay? Because these are indices, you have to add that one extra, right? If it goes from 7 to 7, it's not that there are 0 items, there's 1 item, right? So by looking at the range, I know exactly what the frequency is. And therefore, I figured out that 24 only occurs twice if I'm going to chop at 13. And that's how I figured out what I'm going to pass up the tree. Fine? Same thing over here. We started at position 5. So the range was 3 through 6. So I started 3 through 6, but I was looking for left, not right. So therefore, I'm really interested in 5 through 6, which, if you use the same formula, it's 6 minus 5 plus 1, which is 2. Right?
I was gonna ask if you need to save the ending index for any.
Well, there are lots of savings you can make. You're right. I don't need to keep track of everything, but the more I throw away, the more details I have to take care of in the programming part. So my rule of thumb usually in these cases is to store a little extra information. Later on, I can throw them out if I never use them. Here, since everything is continuous, we're okay. We could get by with a lot less information.
I figured if the ending index is not exactly coinciding, then we
Right.
could use that information.
So another way to deal with this is to say I'll keep track of 1, 15, and I'll remember the breakpoint. So I could say 1, 15, 10, which means if I'm 10 or less, I go this way. 10 or more, I go that way. So I would have all that information right here. I don't have to go there and figure this out. There are lots of variations one can come up with. It all depends on your implementation, and some may be more appealing to you, others may be more appealing to someone else. No? Other questions? So something that's key here is to figure out what information gets stored in every node. And so you have to code this accordingly when you implement it. You have to deal with all that, and make sure that information remains correct and gets and stores all the right information. Okay, so are you convinced that this is not big O of n, that this is log n here?
Yeah, makes sense.
Yeah. Okay. Good.
I was gonna say also those tiny details like adding that +1 because it's an index.
Yeah, those things are, if you've done enough examples, you'll, those are things that you'll take care of automatically. Otherwise, somewhere it'll show up in your debugging that, hey, you're off by 1 somewhere. So figure this out, right? Okay, so what we've done here is to solve this problem where we are. I should put back the time complexities here so that you understand this. This is the time complexity of the tree version. The amount of pre-processing that you apply is still big O of n, because the tree can be built in big O of n time. Actually, the amount of space that it uses is a lot less, because remember, you're only doing this with the unique items. So the tree actually size should be big O of m, but then you end up storing the original array anyway, so you could simply say big O of n. Then the amount of time it takes to answer a query is proportional to the height of the tree. Height of the tree is log of m, not log of n, where m is the number of unique items, right? Because you're building the tree only with the unique items. So that's log of m. And the if you're asking k queries, it's going to be k times log n plus the time it takes to build the original tree. Yeah? Okay with this? So ask me. Slow me down, otherwise I'll keep going.
I don't know where to begin.
Which part? How far back?
Mainly to the 5 and 13.
Uh-huh.
Like at the very beginning where you see the ranges 3 and 2, the 24 and 2.
Yeah.
I don't know how you were able to identify those.
These identify, these two are clear, right?
No, I'm unclear with that.
You're not clear with that.
Yeah.
So, first of all, we wanted to locate 5, the index 5. And we figured out that index 5 comes here, brings us here. Correct?
Because it's in between 3.
Index 5 is in the range 1 through 15.
Right.
Index 5 is in the range 1 through 10. Index 5 is in the range 1 through 6. Index 5 is in the range 3 to 6. That's why we ended up there.
Okay.
It's not there anywhere else. Clear?
Yes.
So, we're here, and this node tells me that this corresponds to 4 copies of the number 3 that sit from locations 3 through 6. That's what it tells us. But our query only starts at index 5. This goes from index 3 through 6. So if I'm starting from 5 and going this way, how many copies of 3 do I have?
2.
I have only 2. And therefore I need to figure that out. And so I have to do some mental math for this, and that's what I was trying to explain here. Once you figure out that 3 only has 2 copies if you start at 5, now I have to figure out how that information gets used. So I work up my tree, and remember, as I go up the tree, it contains information about everything below it. Great. So over here, I have information that says of everything here, 3 is the most frequent item and it appears 4 times. Well, we know that that's not true for us because we are only interested in the range 5, 6. This guy is not even in the range 5, 6, so I'm completely going to ignore it. This guy, I only have 3, 2 because I only am interested in 2 of the copies. So I'm going to say, yeah, even though I wrote down here 3, 4, really the information that I got from below is 3, 2, meaning 3 that appears twice. Then I go up here, same thing. It's got this 3, 2, but there is an entire subtree here that I haven't processed. And that subtree already has everything figured out. It says 9 appears 3 times in this subtree. I don't even have to go and process it, but I can give you that information. So that's where this 9, 3 showed up from. Because this entire right subtree is relevant for us because it's in the range that we are interested in. Remember, it's falling on this side, so it's all useful. Anything that falls on this side is worthless, right? Then I go up here. Well, I'm already at the top. I'm going to take care of that side anyway, so there's nothing to process there. Then when I come here, I see a right-hand side that I'm ignoring, but it's already outside the range. I don't care. I come down here. There is a left subtree. There's a range that I'm interested in. I have to see what's hidden in there. And there it says, well, the most frequent item is 15. It appears once. Okay, so you say okay and note it down. But it's already worse than this, so I don't have to worry about it. Then I go down here, and again I have to do this little juggling around with the 24 because remember I want to stop at 13, and 13 stops right there somewhere in between, which means it stops here, which means it stops after 2 of these 24s, not after all 3 24s, right? And that I figured out, and that's why I have 24, 2, because now I have only 2 copies of 24 that are relevant. And when I use that information, I see that I look at all 4 of these information and I see that 9 is the most frequent item I have to answer, and so that's the answer I give you.
That makes sense.
Okay?
Yeah.
So, and it's useful to imagine that these subtrees here that we ignored, you have to imagine that they're very large, and there's a lot of processing that was pre-processed and given to you without you actually having to do the work. And that's why it's useful.
I have a question. When you're returning the values for like the subtrees, so for
Yeah.
example, on the left side, we ignore 1 and 2.
Yeah.
So we don't even process that.
Uh-huh.
But we still, in like programmatically, would we be still comparing the 2 values from the left and right subtree to choose? And since we don't process the left one, would it be null or?
Which node exactly?
So 1, 6 on the left side.
Uh-huh.
So we don't process the left because it's outside of our range.
Correct.
But we still, like for 1, 6 and 7, 10, there, because we do process both trees, we compare the values to see which has a higher
Correct.
frequency.
Correct.
So that makes
No,
sense.
but I don't have to because it's already written down here.
But I mean, between 1, 6 and 7, 10, for the node 1, 10, you do compare the
I
2
do have to
values that you're
compare.
returning, right?
Correct. Yeah.
But so then for the case with like 1, 6, because we don't process the left side, do we still need to make that comparison, or?
Yeah, so the way this is gonna happen is, I first find my location for 5.
Yeah.
Then on my way back,
Mhm.
I take everything from below and use it.
Mhm.
This information gets passed here.
Yeah.
There's no other information that I had, so
Right.
this still remains, so I still have 3, 2 here. I go up here, from the other side, which was useful, I got 9, 3, that trumps 3, 2, so I can throw that out.
Right.
So I only keep track of 9, 3 at this point. Go up here, and I'm going to go down the other side, so I don't have to remember anything. I go down here, I ignore that, so it's still 9, 3, that's the best so far. I go down here, I'm sorry, I now have to go bottom up. So I start with 24, 2, I go up here, from this side I got 15, 1,
Yeah.
and that gets thrown away. Then 24, 2 stays, 24, 2 stays. I compare 24, 2 and 9, 3 and 9, 3 this.
So you'd only compare the values if you have 2 non-null values, right? Because
Correct.
from like 1, 6, the left subtree would just return null.
Correct.
Okay.
I don't think we talked about it, but what if the nodes are equal?
If they're equal, you pick one, doesn't matter.
But if it's equal somewhere in it doesn't matter what stage.
Doesn't matter, because I never told you, give me the smallest
of them.
value or something like this.
Mhm.
If there were other constraints, then you would take that into account. Otherwise, you just ignore it and say, I'll blindly pick one.
So there's multiple solutions.
Because,
Multiple
yeah,
options.
occasionally there could be multiple solutions.
Or could we
This-
be asked to list all of the numbers that?
Unlikely, because then you will not be able to get the time complexities I'm telling you. If there are multiple ones, imagine that everything has frequency 2, what are you gonna do, right? You just have to go in and list out all of these, and there could be order n of those. So your time complexity of reporting the answer becomes too large, and so your time complexities go through the roof. Okay? All right. So yeah, we already know this. So I'm ready to move on to a new problem because we're sick and tired of this mode and trees. So let me give you a new problem. Okay? I was hoping to get to graphs, but we don't have enough time for graphs, so let's talk about this problem.
Do you have the code, by the way, for that last problem?
You mean like pseudocode?
Yeah.
I never wrote it. I'm hoping one of you will do it.
Don't worry.
We should. You should. Is what I'd say. It's worthwhile. You have all the pieces here, and I've written some version of the code in an earlier slide on one of the previous days. So I'd say hunt it down and see if you can at least write some pseudocode for yourself. It would be what you would really understand it at that point if you do it. Right now, you understand it conceptually. The moment you go home, it's possible that you've forgotten it and it's gone. Okay, that's what happens with a lot of these ideas. So here is find max sum. You're given a, oh no. What did I do? Okay, fine. My animation is all messed up, sorry. All right, please don't look at this naive solution. You're given this array and you're asked, find me the range of, an index range. If you add that up, it's the highest you can get. Should I repeat that? Yeah, that was
Yeah.
really awful explanation of the problem. Find me the sub-array with the highest sum. Yeah? Go ahead.
Just a suggestion, could 2 pointers be used here?
You can use 2 pointers, yeah?
And then, say for instance, you go through.
Right. In fact, that's your naive solution right here. It says for I equals 1 to n, j equals 1 to n, find the sum of items between I and j, and if it's whichever is the largest, just keep track of it and report it at the end. Right? And that's an obvious solution. It's possible it's the best, we just don't know. At this point, this is our first solution, so we're gonna write that down. So you all understand the problem. I can easily solve it by trying every possible range. Clear? Great. And question is, what's the time complexity of this, the way I've written it here?
N squared.
Well, there are 2 for loops, but then compute sum is not all that easy, is it? So it's more like?
N cubed.
More like n cubed, right? Unless I do something smarter. So n cubed is horrible. Who would ever write an n cubed algorithm? So let's try and do better.
Could you look through it once and just add together all the numbers that are greater than 0?
All the numbers that are?
Greater than 0.
Well, you could, but remember, you're looking for a range, and that range may have some negative numbers.
Yeah, but that's what I'm saying. Add together all the numbers that are greater than 0, so all the ones that are non-negative.
How will that help you? I'm still not following you.
To get the sum for that range. No? The
Remember,
maximum sum.
it needs to be an index range. If I say,
Oh,
if I
okay.
say from here to here, you better add up everything, including the negative numbers. So I want a range of indices where the sum is the highest. Anyways, what do you think is the answer here?
Probably on the right side.
24, 2.
Yeah, so perhaps it's here somewhere, right? So that would be 3941, something like that. So it's based on that, your gut feeling says, let's ignore all the negative numbers and get the answer. Well, no, sorry, perhaps it was not clear. You were.
Yeah, I misunderstood the question.
But now is it
Yeah,
clear?
now I understand.
By the way, do you think the final answer may have some negative numbers in the range?
Maybe possible.
Sorry?
Yeah, maybe it's possible.
Maybe?
Like
Can you give me an example where it happens?
From index 3 to index 4. Oh, wait.
Yeah.
The answer for this one is a negative number, I think.
Sorry?
The answer for this one is a negative number, I think. So it has a negative 20.
Yeah, but you're,
We wanna take that.
you wanna take that, okay, he says take that.
Take that, what do you mean take that?
Like the
We wanna have
negative.
it integrated.
But
The
you
way I
don't have
look
a
at it
choice. You have
is
to
that
take
like
all numbers
it's
in
kind of
it.
like a game, and like
Well, we
you
can
can
take
kind of
one.
like take a hit
That's
early
the one
on,
before that, I don't
and it's
have.
possible that like you can extend your subarray to include
Right.
better elements to make
That's
up for
right.
that loss.
So in fact, the right answer here is, as Jian says, you can take a small hit. Minus 20 is a small hit, but the gain after that is much higher.
Yeah.
So really, the right answer is going all the way from 15 through 39. If you do that, your total is
Plus
what?
9.
39, 41, 80, minus 20, that's 60. So I'm getting a total of 60 for the range from here to here. If you had only taken this, you would have gotten 41. So my answer is better, even though I took some negative numbers. So negative numbers are not they're not a death sentence. You could take them as long as later on you could make up for it.
Yeah, I just wanna clarify the question, are we given a index range? and
No,
we have to
you're
find
not
the
given an
actual-
index range at all. You're given the whole array,
Yeah.
and you're asked, just tell me where in this array I can find the maximum sum.
Just wanna say J should not be 1 to n.
Okay.
Even for the naive solution.
Okay, so
Should be
I
from
can make this
to
I
n.
plus 1 to n, right? Because there's no point in not including, in going all the way from 1. If j is less than I, it doesn't even make sense. The sum doesn't even make sense. But even if you do that, you know that this is still big O of n squared, right? It's a slight, it's actually half of n squared, but it's still pretty bad. So we've got to somehow get out of this hole that says order n squared is the best. So far, that's our best. Okay, and so what do I have here next?
Can we use some of the sum that's already been, that you already have calculated? So you don't have to recalculate?
Yeah, so recalculation could help. That could help in speeding up this step.
Yeah.
But it still doesn't get rid of the 2 for loops, which is where the n squared comes in. So even if I did this in constant time, right, I still am stuck with n squared. And I'm saying n squared already is just too much. That's what I'm trying to say for now. Okay? Yes, Usman.
Yeah, I was thinking we have a tree-based solution.
Key-based.
Like a tree-based solution.
A tree-based solution, okay. Yeah, go ahead, okay.
Okay, whereby the first step you have from index 1 to the last index and then
Uh-huh.
whole sum of the array.
Okay.
And then from index 1 to half of
So, yeah, we could do something like what we did last time, where we have a tree and all the n elements are at the leaves and the sums are all up there. But this time, you know, my queries are, I don't have a query. I don't have somebody who says, give me the sum between 3 and 19. Say, I don't care where you look, but find me the largest sum, right? That's what we're asking. So so essentially in the end, you would have to go and query each possible range, which is n squared.
Or couldn't you treat it as one query with I to j?
You could, but there is no I and j.
I mean, you could say 0 to n is the n minus 1 is the query, and which is log n.
Well, so that's why this problem is not a query problem. There is no pre-processing. There's only one processing, and that's to find me the right answer.
Because we have to
Yes.
find the range and not the, we're not given the range, we have to find the
We're not
range.
given
But
a
I'm
range.
saying the range is given as the first to the last.
Sure, that's like saying go look through the whole array. So it's not really a range.
There's this algorithm that I did before. I don't know if it's gonna work. It's called, I don't know, it starts with K. And Danny, I'm not that sure.
Uh-huh.
I think it starts from the back, but I'm not, I've kind of forgotten.
But what I'd like to tell you now is that you don't need any of these fancy techniques whose names you can't remember. What you need is just mostly common sense. Yeah.
I'm not too sure how this would work, but I've got the feeling it's like a monotonic stack or something like that.
There's something monotonic. It's possible. Yeah.
Okay.
The only problem is there are negative numbers, which is annoyingly non-monotonic.
What do you mean monotonic?
So monotonic is when if all the numbers were positive, what do you think is the answer?
The whole sum?
It's the whole array, right?
Mm.
And that's because as you add more and more, the sum is monotonically increasing.
Yeah.
So monotonic is when there is either increase or decrease. That's
Oh.
that's what is meant by
So-
monotonic. Here, well, that's not quite true.
That's
It's
not
like
my-
what Ian was saying, keep it. I think it has something to do with keep it.
Keep it, okay, but how do I know what to keep?
Because you look at the negative, how much are you taking away?
No, look, somehow I have to
Get rid
get
of
this
the-
naive solution out of my head, because that's going to bury me in this hole of n squared and never get me out. So maybe I should take that off the screen there so that you'll think afresh.
Maybe start by finding the largest number in the array and then creating a
I
window.
could find
from
the
that.
largest number in the array, but do you think the largest number in the array has to be there? So imagine that there are mostly 2's and minus 2's, and then somewhere there's a 3. Well, I could put in a string of 2's here that'll give me the largest sum, and then 3 could be so buried in a bunch of minus 2's. That's not useful at all.
Then what about the largest sequence of positive numbers?
Largest sequence of positive numbers. Well, then you're going to miss your 39. If everything here is
Oh,
1 1 1
true.
1 1 and I have a 39, you're gonna miss that.
But so, you can't keep count of like the total of like the window that you're looking at?
I can keep track of whatever I want, but as long as it doesn't cost me n squared, right? Because that's what I'm trying to be.
Couldn't you move through it like the cube where you're like popping one off each edge until then
Uh-huh.
Sliding
you're
window.
having the
Okay.
count?
What did he say?
Sliding window, they say. All right,
Yeah,
that
I was
sounds like an idea.
I
Tell
was
me what
thinking
to do
about
with
a
that.
sliding window. Whenever your sum hits 0,
Uh-huh.
then you move the left
Uh-huh.
point and then and then start from there. Like whenever your point sum hits 0, then you kind of move the window and then check the.
Okay, other thoughts before I tell you a little bit more? How am I doing with time?
I think you're over time. Maybe the
Then-
whole, start with the whole.
Do you wanna think
conversation.
about this problem,
Yeah,
or
we
do
should
you want me
think
to
about
give
it.
you some hints? What do you wanna do?
I know what it is.
Let's think about it.
Sorry, you wanna think about it?
Yeah.
Think about it, yes, fine, okay, you have some thoughts.
Okay, maybe we keep track of the position of the negative side, and then we add up the positive numbers, ignoring the negative ones,
Yeah.
and we see if the cost is good enough, for example, the 20, for the summation to be.
Yeah, but I don't know where to start. So you're saying go find the negative numbers and then
And then
what?
we add up any other positive.
Well, so
values.
how is that much different from finding the largest positive and searching around there, or finding the largest negative and removing things from there? Are these techniques going to help you a whole lot?
Mhm.
Unclear.
What if we start with the whole range as the,
Okay,
as
good.
the sliding window?
Excellent.
And then move on both ends to see.
What would be your decision whether to move each foot
It
in?
has to change in the positive direction.
Negative direction.
No, I mean the sum
Ah,
has to be
okay,
more,
okay.
is higher,
Uh-huh.
higher for you to move the window.
Yeah, but what if I encounter a lot of, wait,
So you have
you,
layer
by
one.
removing it, you want it to increase?
By moving the window,
Uh-huh.
I will,
Yeah, so, I could put a couple of positive ones at either end, and then you're stuck forever.
yeah,
So, yeah, we need.
start in the middle.
I can put a whole bunch of negatives there and mess you up. Tell me where you're gonna look, and I'll stick in a few negatives there, right? That doesn't help me.
Couldn't we just start from the very beginning?
Okay, so good thing is that we convinced ourselves negative numbers are not poisonous. They could still be part of the answer, right? Are you fine with that?
Yeah.
Okay, so you're gonna say something?
Yeah, I was
You're
gonna.
still unclear about the negative part?
No, I was gonna say, would it be possible to try to pick a random number and we decide on which side is it?
Yeah, take a gun and do some I don't mean to be frivolous, but the point is that if you try any random approaches, you're going to, you have to worry about two things. One is, are you sure you're gonna get an answer? Because if you don't get, if at the end of a lot of this random work, if you don't have a real answer, then you don't have an algorithm. The other thing is, you also have to worry about, is it possible that just because of my random choices, I get wrong answers? And so if you can answer both those questions, perfectly fine to use random numbers. Okay. Yeah.
I think this will get shot down, but why don't we just just go through it from the very start? So then,
Okay,
and then
yeah,
just keep
fine.
running some.
Yeah,
Once
I've
we-
got 21 and then I got this minus 13. What do I do now? Tell me.
We save the current.
Okay, I got
so
8.
four,
Then-
right? Huh?
Go ahead.
We save the current length because that's what we want, right? We
What if
want
I
the
have,
range.
what if I start with a negative? And I
Then
don't know what to do.
It doesn't really matter because.
Well, you can skip a negative, you can start with a negative.
Yeah,
You don't wanna go into the negative, so you skip out.
What if the negative is better than one?
We never.
Yeah,
So-
well, yeah,
What
but
if
it
the one
could,
is a
the negative still could be the highest value.
Yeah.
So,
If it's all negative.
as you go home today, let me give you some thoughts to think about, okay?
Good point.
Here are some things for you to think about. Imagine that your final answer is some range, let's call that L and R. Let's say these are your magic numbers that give you the answer. Okay? We don't know what it is, but there is an answer, L and R, right? What properties does this piece have that makes it the right answer? That's what you want to think about. And then we could try to make sure that those properties are satisfied. So this is a very different way to think about it, but I think it'll hopefully get you somewhere.
Like,
Okay?
when you say property, is it something like the largest number should be in the range? That is a
Well,
property.
let me ask you simple things, right? If this is the right answer, what do you think L minus 1 looks like?
Negative?
Should take away.
Negative? Are you sure?
Yes, yes.
If it is positive, it will only increase it, right? So it
Yeah.
has to be negative. Great. So I found something. It has to be two negative numbers. Ooh. So let's keep going with this. Is it enough that it's a negative number? Of course, we know it's not enough because negative numbers could be in our answer. So what else is there?
The least negative.
So anyways, I'm giving you ways to think about this so that you could then rethink. This naive solution needs to be dumped. Okay? You need to erase that from your head
Can I say
and
something?
start to think in terms of these properties.
Can we store the indices of the negative numbers? And then only
You'll
check-
find that doesn't really help you.
No?
No, well, again, that won't help you in where I'm leading you. Because I'm saying, if this is your answer, tell me all the nice properties it satisfies, because then I could use that to look for those properties, okay? It's not gonna help you in that abstract thinking, but knowing where all the negative numbers are isn't very useful, because I can throw in a lot of negative numbers. In fact, I can make every alternate one a negative number, but it could be a small negative number and it doesn't hurt you anything, except that they're all over the place and they will mess you up, and your algorithm will end up handling way too many messy things that don't have any relevance to the answer. Yeah.
Okay, what about you start with the sliding window, 17, 14,
Uh-huh.
negative 13, that's still positive. If you add negative 13.
Sorry?
Like if you start a sliding window.
Yeah.
17, 14, negative 13. And then when you hit, right now the sum would be around, the
Yeah.
maximum sum would be
Yeah.
17, 14, right?
17.4, okay, that's
Yeah,
fine.
17, 14.
Uh-huh.
Then you hit negative 13.
You wanna keep that, right?
Yeah, but you keep the
For now.
maximum as.
Okay, you wanna keep the -3?
Yeah, then you keep the minus, then the sum becomes negative 0 or less than,
4 and 4, 8, it's still positive.
it's still positive. Move then you add a
Yeah.
9.
I think you move the left pointer
Yeah,
whenever
drive
your
carefully
count is
because this
below
is a
your
nice
lowest
problem to think
total,
about.
like, ever count. So like you keep track of what your max count's been, and whenever your count's been goes below your max count, then you move the left pointer over. So that we can start using.
Convince yourself of that first.
Yes.
Shall we stop here?
Yeah, okay, so.
You guys don't wanna go
It's a
home?
good problem